Today, I'm going to be talking about another theorem used in the mathematical statistics, and this is the Theorem of Lehman-Scheffe. To start, again, I'm going to give a little introduction about this theorem. And well, in statistics, the Lehman-Scheffe theorem was named after Eric Leo Lehman and Henry Scheffe. And this theorem states that any unbased estimator based only on a complete sufficient statistic is the unique best unbased estimator of its expected value. And the Lehman-Scheffe theorem is a prominent theory in mathematical statistics, tying together the ideas of completeness, sufficiency, uniqueness, and best unbiased estimation. These are concepts that are related to this theorem. In the definition, we have that we suppose that Y is a sufficient statistic for the parameter theta. We say that Y is complete if there are non-trivial unbased estimates of 0 based on this statistic Y. This means that the expected value of the function g depending on Y is equal to 0 for all values of theta. And then the probability of the function based on Y is equal to 0, and all of this is equal to 1 for all values of theta. And if we have two unbased estimates of theta that are based in the statistic Y, we say that these two values, the differences between these two values, the expected value of the difference between these two values that are shown right here is equal to 0 for all values of theta. So that regardless of theta, both values coincide that they both have the probability of 1. So if we find one unbased estimate of theta based on the statistic Y, we have essentially found all of them. And well, just as in the Rao-Blackwell theorem, this Lehman-Scheffe theorem this result holds equally well if we are seeking an UMB-UE of a function of theta. So we look for an unbased estimate of the parameter theta based on the complete sufficient statistic Y. The theorem says that we suppose that this statistic Y, we're going to call this statistic Y1, is equal to the vector U1 from x1 to xn, and is a complete sufficient statistic for theta. If this parameter is an unbased estimate of theta based on this statistic Y1, then among all possible unbased estimators of theta, this same value has minimum variance. We say that this value is a uniformly minimum variance unbased estimate of theta. That is what we called before UMB-UE. The term uniformly is used because the result holds for all possible values of theta. Well, to finish, this theorem is a consequence of the theorem Rao-Blackwell, and one can easily extend this theorem to the case of the uniformly minimum risk unbased estimator under any loss function. What we have with this theorem, this is essentially to understand the Rao-Blackwell theorem. And here are the references.